Welcome to Mathematica for Biologists, Chapter 1, Part 4. Okay, in the previous tutorial, we learned how to take data from any given animal and average that data at each time point and come up with a plot like this, where we have the center line is the mean of those three replicates from that one animal, and then the lower dotted line is minus standard deviation, and the upper one is plus standard deviation. So that involved a lot of code, so we'll review that and then we'll actually compact that into and make a function that does that code, so we don't have to replicate it multiple times, so we can make our grand plot at the end. And delete that. Okay, as we've been doing before, we're just going to open up by pointing to the file, and then we're going to load up data. This time, this is just as before, we're going to call the data capital data, because we're loading all data from all species, and this is in the Microsoft Excel spreadsheet. So you don't need to have Excel installed. Mathematica will parse the file, and its code word for parsing out the file is data. So this is the line you want to type in to load up those data. Okay, so I'm going to load that in, and then checking the dimensions of the data. Here we see it's 100 rows by 4 worksheets by 9 columns. So the 9 columns, again, that's our 1 through 3 replicates for each of 3 animals, and then 100 rows of time points, and then 4 worksheets, 1 for each of 4 species. So this isn't a very convenient data format, actually. It's actually very difficult to work with. So I'll show you just a way to navigate through that data. So let's say we want to isolate one worksheet data, so WS for worksheet and data. And so that equals data that we're going to index, double square brackets. So remember, our data dimensions were 100 by 4 by 9. So first thing we want to do is get all 100 rows, so 1 through 100. And then we want, let's say we want species 1, so that would be 1, the middle index. And then the last index is all 9 columns, so columns 1 through 9. So that'll give us one spreadsheet worth of data. And then dimensions should be 100 by 9. And remember, that's backwards from what we want. We don't want 100 rows and 9 columns. We don't want 100 columns and 9 rows. We want the other way around. Transpose this. So there we go. That's what we want. And just to make life a little easier, species will just be a variable. Let's say we want species 1. Put that in the middle. So hopefully you understand how that works. It's a 3-dimensional array for rows, worksheets, and columns. Alternatively, you can use shorthand. We're going to use the same structure. So we need our transpose command, double brackets, but instead, oops, should be double brackets, single brackets, double brackets here. So we want to index out all rows and just the one for species, and then all columns. So that's an alternative way. You'll get the same data. So now what we want to do is generate a function. So we want to make a function whose output is mean plus or minus standard deviation data through time for a given animal. considering the variation between its replicates and a given species. Let's say individual animal. And okay, so what that's going to look like is, it's easier just to make a function. If you're, you can just make a simple function, for example, just to review, arbitrary function, whatever name it is. You always have square brackets, and then equals, oops, semicolon equals, and then the argument, or a list of arguments. Argument 1, argument 2, for example, and there's always an underscore after the arguments. Okay, so this function will say argument 1 plus argument 2. And that's what that does on arbitrary 1 and 3. We got 4. So that's all a function does. We're going to make a much more complicated function. So the function is called getData. And our first argument is the workbook data from Excel. So that would be this data variable right there. And then the second one is species. And so that's which worksheet to pick. And then individual animal. Individual. And I forgot my underscore for species. So colon equals. And then what I'm going to do is I'm going to do something else which makes my life easier. I'm going to put this all in a module command. And separate the brackets because we'll need multiple lines. The module command just has 2 arguments. The first argument is a list of variables that you define, and the next set of arguments is just whatever you want to do in your function. And the module just says, for these local variables that we list, they only stay local to the function. They don't get confused with things going on outside of the function. So it just makes it more compact, easier way to deal with things. Okay, so one thing we want to do is define a local variable WS data, worksheet data. And so the first line in our function will define that. WS data equals just our line from up here. Transpose. And this is green because it's looking for the species that we define as an argument. So that's WS data. Now we also need which time point we'll look at, because we're going to average at every given time point. So time point, and we're going to need a table here. And so I'll just do this, equals, well actually let me not do the time point right now. Hold on that. We're going to do another variable called mean data. So that's the mean data at all time points. So that is the table command. Equals table. So there's going to be a table command within this module. And of course that table has an iterator. And I'll call that iterator ITR1. So in the table command, I need to know my time point, as I did before, and then equals ITR1. That's our iterator. And then we also need some kind of slice. So before, let me just explain this from the tutorial before. Just as a shorthand, it's easy to keep track of which columns are which in the data. So columns, so I'm just going to call this A for animal. So the first item in this list is a slice command, 1 through 3. This will become obvious in a second. 4 through 6, 7 through 9 for slicing. So for example, if we want animal 1, we would go A1, and that would give us the slice command that would extract out columns 1 through 3. So slice, and that's another local variable we need to define. Slice equals A, which we defined up here, and then the individual animal we want. And that should make sense. And then now we want replicate data. And that's another variable we want to define. And so again, that's just all our values that we want to average together. And this is review from last time. So we want to slice out of this worksheet data our slice, which is columns 1 through 3 or 4 through 6 or whatever, getting out all the data for the appropriate animal, or the appropriate data, for a given time point. So this gives us 3 values, 1 for each replicate at a given time point. And as you'll probably notice, I forgot to fill out this part of the table command. So iterator goes from 1 to 100, so that's the number of data points. So the last thing we want to do is actually take the average. Mean equals, mean data equals mean of rep data. And we leave that semicolon off. And this function's not done yet, but I'm gonna test it. And I always like to do an output variable. So output equals mean data. So I'm going to do Shift Enter to initialize that, or instantiate that, get data. Let's try this. Workbook data is data, our variable. Species 1, for example. Individual, let's just say animal 1. And what I should see is just one column of data, and that's mean data. And so I'm going to plot that. And it should look like the correct, typo. And that looks correct to me. And so I can change the individual from 1 to 3, or I could change the species from 1 to 4. So it's just looking at the right part of the data. Alright, that's cool. That's almost there, not quite fully what we want. So let's go back and continue to work on this. Alright, so that's our mean data, but also what we need is we need standard deviation data. So I'm going to put that after. It doesn't matter where you put your variables in here, SD data. So SD data equals the same thing. I'm just going to copy this table command. Same exact thing, except we use the standard deviation. Of the same thing. Okay. And that should work because the previous one worked. So all we have to do now is combine everything at the end. So I'm going to say, oh, by the way, I made a mistake before that I just caught. So remember when we copy pasted this SD data? We want to to fill this with, we want to replace this with SD data, otherwise it won't work. Okay, so now what we need is gather the output at the end. This is easy, so we want mean plus SD. So I'll put that up here. And we also want mean minus SD. And that just equals mean data plus SD data. And mean minus SD is just the same. And then now, in our output, we just gather everything together in a list. Because remember, we want to dump all this data output from this function into a list line plot command. So if we want 3 plots, we need 3 sets of data, 3 columns of data. So one column, the first column will be this mean plus SD. Second column will be the actual mean data. Third will be mean minus. So here we're building our list. Mean plus SD. Mean data itself. Mean minus SD. And no semicolon there. So I'm just going to test this, test the dimensions of it. Get data. Put in our data spreadsheet. Sorry, that was double brackets. It should be single brackets. Data, and then species 1, individual 1. And the dimension should be 3 by 100. Forgot to initialize this. 3 by 100. Okay, good. So don't forget to instantiate your function by doing a shift enter. So if I do a list line plot, we get everything. So that's great. So now I'm going to show you how to use this function to plot all of our plots and make that nice plot that I showed you way at the beginning of this set of tutorials. Now here is where Mathematica gets really, really powerful for graphics. And I know no other programming platform that can do this easily. So we can make an array or a table of graphics very easily. So I'll demonstrate that. So let's make a table of plots using a table command. And we're going to put our get data thing inside of that. And remember, all we have to do is say list line plot. So it's a function within a table command. And we're going to make this, for example, for all the individuals. For individuals 1 through 3. So inside this we'll say get data, single brackets, using our overall data and the species that we want, which I'll say 1 in this case. And then for an individual, we just use our iterator, which we've also called individual. So for each for 1 through 3, it'll go and make these plots. So if I run this, we literally get a table of plots for 3 individuals. So that's really, really cool. But that doesn't look very nice because it's literally just a list of plots. It's not really graphics objects. It's a list of graphics objects. So one thing we can do is we can use another command. So I'm going to call this plot table, table 1 for species 1. And then use this really, really nice command, graphics column. So graphics column. And if you put in a list into graphics column, it just makes a column of graphics, which is itself an overall graphics object. So now it looks really nice. So this whole thing can be saved as a graphic, so saved as a JPEG or PDF or whatever. So this is information from species 1, or species A, for our 3 individuals, which is great. It's exactly what we want, mean plus or minus standard deviation data. So now, all we have to do is copy this 3 more times for each of our species. 2, 3, 4 for species 1, 2, 3, and 4. And I'll just make a comment. Species A, B, C, D. So we can just call this graph call 1. So we're making a list of 4 graphics columns. 1, 2, 3, 4, and the same over here. So we have that all stored together. And then, as you might have guessed, there's another wonderful command called graphics row, where we can just list together all the graphics columns together. 1 graph, column, 2 graph, 3. And we don't see anything, and that's because we actually didn't define the size of the graphs. So all we need to do is change the size of the plots, and we can define that up here in this list line plot command. If you click on something twice, it'll highlight everything under that command. So this list line plot will have arguments, so we'll just say image size, which happens to be the right command, and then arrow size, which is another variable we'll define up here. Size, let's say, equals 100. I'm not sure whether that's going to be big enough. Copy that 4 times. And now this should work out to be something more manageable. And then 200 actually is quite almost perfect. And you can tweak it as you wish. Okay, so that's exactly what we want. We have individuals 1, 2, 3 for species A, B, C, D. Let's make some labels, actually. So we're going to actually put a lot of arguments on these plots. So here are the plot arguments. We'll say plot label. For this first one, it's a string, species A. Copy that again. And actually that looks silly because it's labeling every single one of the plots. So I'm going to get rid of that, and I'll show you how to deal with just labeling each column. And you can probably guess what I'm going to do. I'm just going to label it down here. Plot label, species A, B, C, D, just for each column. So that's great. So now we need axes labels as well for everybody. Axes label. And then remember that's a list. So we're doing time versus speed. And so that'll do everything nicely for every plot. And there we go. So that's labeled. So let's do some styling on the actual graphs. So I'm going to write something called style inflow. And this is from the previous tutorial, but I'll review that. So again, what we want to do is have this center mean line be different from the standard deviation lines. So what I'm going to do is we'll make a list for our, each is going to have 3 plots, so 3 lists, and it's really going to be 3 lists within lists. So make those, because each plot has a different characteristics. So we'll do a variable which I'll call SD color. And so the SD is the first and last one, SD color. And the middle plot, remember, is mean color. And we want the mean line to be thick. And we want the SD lines, let's say they're dashed, just for fun. And to define the colors, mean color, let's go down and do that in an empty part of the workbook. So remember, we're going to use this color setter trick that I showed you before in the previous tutorial. Let's maximize the window here. And so I did that command, and then I'm going to copy paste this block of color and say setting. Okay, so that's my interactive color control. Copy that and paste that into mean color. And do a semicolon, and we want an SD color, define that. And it's another semicolon. And for mean color, let's do some nice blue, thick blue color. And then for SD color, let's do a lighter blue color. And that's cool. Okay, now all we have to do is in these plot arguments, plot style, make a little arrow, equals style info. And do that for everybody. And the graphs will start to look really nice. Alright, cool. We can start to see how things are shaping up. Okay, now just a few more little modifications. One thing I'm going to do is I'm going to make something called filling. So in our original graphs, we actually filled in, we shaded in between the 2 standard deviations. It just makes it easier to see if you're making a publication quality figure, because you can still see the standard deviation depending on different kind of printers. So we'll do that. We'll call this filling info. And this is kind of a weird command. You just have to use it and get used to it. So we want to fill between plots 1 and 3. And this is the correct notation for this. And you'll just have to play with it on your own if you want to really learn how it works. And define some fill color. Close out that list. So this is filling info. We'll do another fill color up here. Let's make this a light blue. So it's not too crazy on the eyes. Okay. So now all we need to do is, as you could guess, filling. I think filling is the correct way to do it. Yep, filling is filling info. Copy paste that. Bear with me. Here we go. We're starting to Yeah, now we're really starting to see some really nice looking plots. Almost done. So one thing we want to do is modify the text. So I'm going to say text info, and this is going to be another list, and it will say font family, call this times, it's pretty standard, and then font size, let's try 15 points. And then the argument to use for that is called base style. Text info. And all these things you can learn more about tweaking if you go into the help for these plot commands. So if you highlight the list line plot command and F1 and go into the help, you'll see how to do all these things, and I've just learned how to do it over the years. So we see that looks great. So another thing we need to do is actually label our plots, because we can't tell the difference between the plots within these columns. That's slightly trickier because the plot labels change depending on the plot. So we have to do it programmatically. So, but that's pretty easy. We just learn a new command. So here we start a new argument, plot label. And if it were just constant, we would just write some string there, and that would be a constant string. But it's not constant. It depends on individual. So we'll use a new command, string join, which puts strings together. String join, and the first part of the string is animal number. The second part of the string is the actual individual, which is not a string, it's a number, so we have to change it to a string using the toString command. Which is just our iterator. I believe that's correct, and I'm just going to try to do that just for one column, see if it works. And it does work. So I'm going to copy that. Actually, that number sign looks a little bit hokey, so I'm going to get rid of that. And now I'll just copy paste my plot label command for everybody. Be careful of your brackets. Don't mess up the structure. Okay, there we go. And now just one little adjustment. You'll see that on the speed there's too many divisions. It's just difficult to look at. So we can clean that up using this command called find divisions. So for example, if you have some kind of range between two numbers, and you want two divisions between it, it'll generate those divisions. So that's great. So hold that thought. What we're going to do first is we're going to define the ranges of our plots. So, because you'll notice that these plots have different ranges. So we want to compare them more easily just by eye. So I'm going to define a range up here. Cancel that. Range equals, and I did this by trial and error before just to make it look good. So plot range is min and max for x and min and max for y. So min and max for x is easy, it just goes between 0 and 100. For y is a little harder, but it turns out to look good if you do 0.2 to 1.2 for everybody. And then as you guess, that's just another argument, plot range, and we'll do that for everybody. And I keep on saying we're almost done, but now we're really almost done. Do that, and then everybody should be scaled to the same scale so we can compare them easily. That's just an example. And now we need to get rid of the extra ticks. Remember that find divisions trick before? And what we're going to do is, remember the range that we defined before, we want to do between a range. So if we replace this with range, the second argument of our range list, the second element of our range list, and let's say we do 5 divisions or so, then it'll come up with that. And so we can say number of ticks equals 5, for example. I'll copy paste that in. And Mathematica is going to do something annoying, which I'm anticipating already, which you'll see. But anyway, I'll show you it just as an exercise. So number of ticks, and then I'll just call this ticks equals that. Okay, so we have our ticks there. So we'll write ticks info, and this has to be a list because we have to define it for the x-axis. And their automatic labeling was fine for the x-axis, it was just looked bad for the y, so I'm just going to say we're going to use our substituted values. Okay. So now we just add another argument, ticks, info. I'll do that for everybody, of course. And you can see how we have fewer ticks, but it looks terrible because it's in fractions. And so that's kind of a Mathematica annoying thing, that if you need to tell it the precision of the number. So in order to force it to have a floating point kind of operation, just multiply your ticks by 1.0. And then that will hopefully fix everything. Great. So that looks great. And we can add more ticks if we want. 6. But I think 5 look pretty good to me. And that looks like it should conclude our tutorial. So that concludes chapter 1. So hopefully you've learned how to get data in and out of Mathematica and save that data, manipulate it a little bit. You've learned how to manipulate lists. You've learned how to build tables and index the table data from the tables, index arrays and things like that. You've learned how to make plots and really make kind of more artistic looking plots. And then just for completeness, let me just export this so you know how to do it. Just call this big capital G for a graph. And we'll export it to wherever you've already defined it. So export big graph dot SVG or whatever you want, G. And then that's exported.